Thank you very much. So this time we'll do the Euler class. And we'll start with the Euler class in algebraic topology. So let's let X be a real manifold of dimension R, dimension D. And let's let V to X be a rank R vector bundle. Then V is oriented if it's equipped with a Tom class.
Sorry, I don't know if this is me, but I can hardly hear you.
Oh, so I'll speak up.
No, but maybe you need to adjust the position of the mic.
Got it. So, oh wow, yeah. V is oriented by a Tom class. Sorry. And so, actually, I wanted to, by you, a Tom class, and I wanted to recall that the Tom space of V could be defined as the projectivization of V plus a trivial bundle over the projectivization of V, or V over V minus the zero section. And it's oriented by a Tom class in HR, if it has a class in HR of Tom V Z, such that the restriction to the Tom space of each of the fibers, so for example, the Tom space of the fiber over X is just the projectivization of the vector space X plus a trivial factor over the projectivization of Vx, which is a sphere. And so what a Tom class is it's a class in here, so i.e. a class in here, which, when restricted, to the cohomology of the Tom space of each of the fibers, you get a generator. So an example of when you have an oriented vector bundle is if all of your transition functions have a positive determinant. So suppose U is an open cover of X, and V is described by transition functions or clutching functions. Phi at the intersection of two of these open sets for U and W in the cover, such that at all the points, the determinant of this linear map is greater than 0. And if it's greater than 0, we can take a square root. And if we take the positive square root, the cocycle condition is still satisfied. So this is if and only if V is isomorphic to the tensor square of some line bundle. Sorry, if the determinant of V, where L over X is a line bundle. Okay, so then X is oriented if its tangent spaces. If X is compact, and so assume X compact, and that the dimension D is equal to R, Poincare duality gives us an isomorphism from HR of compact, oriented, still a manifold. Poincare duality gives us an isomorphism from the dimension D cohomology of X with Z. So we can assume, under these assumptions, E of V is an integer. So we can compute this class as we did in the first lecture. So we can say that E of V can be computed as follows. If you choose a section sigma with only isolated zeros, E of V is the sum over these zeros of the local degree of the section at X, where we first identify sigma with a function. So this is the local degree, and where sigma is identified with a function from the manifold to is locally to RR by choosing local coordinates and a local trivialization compatible with the orientations. So if you took this, the sphere inside each of those R to R's, with its standard orientation from R to the R, it will agree with the one coming from the Tom class, compatible with orientations. If we composed our trivialization with something, with a new element of GL of U, and it had negative determinant, we would change this local degree here, so that wouldn't make sense. But if we changed both of them simultaneously, both the coordinates on X and the trivialization on R, we would still get the same answer. So we can do the same story with a relative orientation. So I wanted to write that down. Remark, if we change both the coordinates and trivialization, local coordinates and local trivialization, by a matrix with determinant less than 0, the degree X sigma does not change. So this leads to a notion of relatively oriented. So we'll say that V to X is relatively oriented if the Hams from the tangent space if Ham of what matters is the determinant of the tangent bundle to the determinant of V is oriented. So we know what it would mean for such a homomorphism to be positive, and then we won't change the value of the local index. So V has an orientation sheaf. So let O of V be the local system on X. With fiber at a point X equal to the cohomology of the Thom space of Vx at Z, and you can run the previous discussion of having a Thom class using a Thom isomorphism. So we have, and it's in the notes, an Euler class, EV, and HR of X with coefficients in the orientation sheaf, coming from canonical map. Let's say coming from a canonical map from the Thom of the negative V 2x and a Thom isomorphism, and it's written down carefully in the notes, and maybe we'll put a minus V there. And then when V is relatively oriented, we can again view can have E of V as an integer, which can again be computed as a sum of local indices, which is again well defined because we have a notion of changing both at once. And I think that's all I wanted to say about the Euler class in algebraic topology. So let's move to A1 algebraic topology. So the manifold becomes X a smooth scheme of dimension D, and V to X is an algebraic bundle of rank R, and we're going to define oriented. So V is oriented by the data of L over X, a line bundle, and an isomorphism between the determinant of V and L tensor square. And again, the X will be oriented if its tangent bundle is oriented, and V will be relatively oriented by the choice of an orientation of that same Hom. And V is relatively oriented as before. In fact, I don't even need to write that because it's, V is relatively oriented by the same definition. Okay, so let's do some examples. So Pn, or the Grassmannian of M planes in Pn, so parameterizing Pm's in Pn. Then the determinant of the tangent bundle is the dual of the tautological tensor n+1 times, or for the Grassmannian, you put it in the Plücker embedding and you pull back the O of 1. So in both cases, we'd get this. So we get to conclude that, so if X is Pn or this Grassmannian, X is orientable if and only if n is odd, because then we can take the O of n+1 over 2 and pick just such an isomorphism. So in particular, on P1, we're relatively orientable if and only if we're orientable. So ln over P1 is relatively orientable if and only if it's orientable, if and only if it's even. Another example, and this example is important for Stephen McKean, who is here. So if we take O of D plus O of E on P2, P2, 2 plus 1 is 3, so this is relatively orientable if and only if D plus E is odd. And he uses this to make an analog of Bezout's theorem on intersection of plane curves of degree D and E. So let's talk about computing Euler classes for relatively orientable bundles. I'll let Stephen tell you about his cool theorem as opposed to trying to tell you about it right now. So let's let X smooth proper dimension D equals R, and V over X rank R. And this perspective is joint with Jesty-Cass. There are earlier perspectives, and the first is by Barge and Morel, and we'll do those, but we're going to start here. And we'd like to be able to do the same trick of identifying a section with a function and taking its local degree. So let's give ourselves sigma, a section of V with only isolated zeros. We're going to define the Euler class of V as a sum over the zeros of sigma of a local degree of sigma at X, and so we need to define that local degree. We're going to do it exactly the same way as we did before. We need to have a function, and to have a function, we can choose a local trivialization and local coordinates. Knežević coordinates near X are the data of an atoll map which induces an isomorphism on the function field, so such that the induced extension of residue fields, K phi of P, inside K of P, is actually an isomorphism. And we'll say Knežević coordinates determine a distinguished section of the tangent bundle, and in particular its determinant over U, because we have a nice standard basis for AD. A local trivialization let's say it's on all of U, we could shrink U of V over U gives a distinguished section of determinant of V over U, and the coordinates, the local coordinates, and local trivialization are compatible with a chosen relative orientation if the distinguished section you get, homming the first to the second, is a tensor square. Of hom det Tx to det V is a tensor square. So we can choose compatible local coordinates and local trivialization, because we can just change the trivialization until we get a square, so that's no problem. Getting Nisnevich coordinates, if K of P is a separable extension of K, they always exist. If the dimension is 1, they always exist by a fun Galois theory exercise. Let's say we have them. Then, so suppose phi and psi are compatible local coordinates and local trivialization. If our X was actually covered by affine spaces, so if psi was an open immersion, if phi U is just an open immersion inside affine space, then sigma is indeed a function, because all of the, so then the section sigma can be identified with the pullback function A of D to A of R, and we can let the degree P of sigma be the degree of this. We can just define it as the local degree of this function in the previous sense. So there would be our definition, and if it's not actually necessary for, so this assumption isn't necessary because the A1 local degree is finitely determined, which means that if we modify a function by something that in a high enough power of the maximal ideal, it's not going to change the degree. And so if we've got some a tall map here where the local rings are not isomorphic, we could fail to have our function sigma be pulled back from A of D, but we can add something in a really high power of the maximal ideal, and you can show that then it is pulled back from A of D, at which point we do get a function like this, and those choices will not affect the outcome, the resulting definition, by sort of finite determinacy of the local degree. All right. So then this we add all these up, and we get some sort of Euler class in the Grothendieck-Witt group. And we need to show it's well defined. I'm not going to choose to do that during the talk. So it's well defined under conditions. Instead, let me give you some meaning it doesn't depend on the choice of section. Let me give you other perspectives on the Euler class. Barge Morel has an Euler class V in the oriented Chow of group in degree R with coefficients in the determinant of V or minus V. It won't matter because since the action of the growth unique bit group has these squares being trivial, and our definition of the twist for oriented Chow groups, which went by a little fast a couple lectures ago, but that does mean that changing the twist by a square of a bundle does not do anything to oriented Chow groups. So they define this as follows. So we have a distinguished element 1 in oriented Chow of 0. And where did that come from? This was computed by a complex, Z in codimension 0 reduced irreducible subschemes of X of GW of K of Z with twist by the determinant of the tangent bundle. And then mapping to that, which goes away. So anything in here gives a distinguished element of oriented Chow, and this goes away because it's the generic point. So we just have a 1 sitting in the growth unique bit group, the angle bracket 1, and that's the distinguished element. In the algebraic topology definition of this Tom class, I mentioned there's this canonical map from a Tom space of a negative V to 2x, giving a kind of a Tom class in H upper 0 of Tom of the negative bundle, which under a Tom isomorphism gives something in HR with this twist. That Tom isomorphism is like the following push forward. So if we let sigma denote the 0 section, then we've got a push forward map from oriented Chow. There would be a twist by the canonical, but we can pull back the canonical, and then when we pull it back again, it'll go away to the oriented Chow. The relative dimension is now the rank R of V, and the sort of difference between the canonical bundle of V and this twist we had to do to get rid of X is like the difference between the tangent space of V and the tangent space of X, which is when you take its determinant, it's the determinant of P star of V. And then P star itself gives an isomorphism from oriented Chow R of X with coefficients and determinant V to this group here. So what we can do is take the push forward and we push forward, and then we view that element inside here, and we get this Euler class. And then when V is relatively oriented, we have some map pi, and we can push forward E of V, and it'll land in the growth unique bit group of K. I should speed up. So there's a different perspective of Morel giving an Euler class that's a principal obstruction to having a non-vanishing section. Those are known to be equal to this one, at least up to a unit, some sort of bracket A, by work of Aravind Ashok and Jean Fazel. and also work of Mark Levine, and it's harder than you would think. There's a six-functor formalism perspective of de Gliese, Jin, and Kahn. Mike Hopkins eyeballed, after a talk I gave, another perspective, and Jean-Pierre Serre and Arpan Raksit, who's also here, noticed that one as well, and it's in a paper of Raksit and Levine, and we've got tools. So let's do some example computations. Example, let's let n be even, and then if we take over P1, the O of n, this can be thought of as the bundle of all meromorphic functions that have, at worst, a pole of order n at some point. Let's say it's 0, and then in terms of local coordinates, the function 1 looks like x to the n. So this becomes the local degree, say at 0, of x to the n. This was one of the examples we did when n equals 2. We found that this was h last lecture, and it's always n over 2 times h. Moreover, because it's a line bundle, the same argument that says Euler classes of Euler classes in ordinary algebraic topology for odd-dimensional vector bundles or two torsion says that this is a multiple of h, and that's a result of Mark Levine. Okay, so as the next example, let's get back to numerative applications, and let's ask, how many lines meet four general lines in P3. And I'm going to follow joint work with Padma, who is here. And also see this is also in Matthias Wendt's Schubert calculus paper. Let's think about this question. The notation for Grassmannians is still that Grassmannian 1,3 parameterizes lines in P3. This is equivalent to W. We should really vary the field for the field of definition of W, but I hope you'll forgive me. So W dimension 2, dimension W equals 2. So the goal of this question is we're going to simultaneously do something fun with a fun answer, and to see how one could calculate, give another example of calculating an Euler class with a bunch of sums. So it's going to be a little explicit, but hopefully still amusing. So let's let L1, L2, L3, L4 be four lines, no two of which intersect. If we just pick, let's let E1, E2, E3, E4 be a basis of K4 such that the line L1 is the projectivization of the span of E3 and E4. So equivalently, if we let phi1, phi2, phi3, phi4 be the dual basis, then this line is given by the vanishing of the two equations, phi1 and phi2. Let's find a condition in terms of some sort of bundle for lines which intersect L1. So let's let L be some other line, the projectivization of K of a span of two vectors. We'll call them E3 twiddle and E4 twiddle. So these are just linearly independent vectors. So if we wrote out E3 twiddle and E4 twiddle in terms of E1, E2, E3, and E4, we need to find some combination so that the first two coefficients, the coefficients of E1 and E2, vanish. So they need to be that there needs to be a linear dependence between the part of their basis expansion having to do with those first two. And it follows from this that L intersect L1 is, they really intersect if and only if when you take phi1, phi2, wedge phi2, and evaluate it on E3 twiddle, wedge E4 twiddle, you get 0. In other words, we could look at this line bundle again. So let S dual wedge S dual over the Grassmannian be the vector bundle, and it's a line bundle, whose fiber over the projectivization of dimension 2 subspace is the dimension 2 subspace dual, is W dual wedge W dual. Then the phi1 and phi2, and I'm going to be a little sloppy and say L1, which is not quite fair, determines a section. Let's be fair. So phi1 and phi2 determine a section of S dual wedge S dual by, let's call this section sigma 1, by sigma 1 is phi1 restricted to W, wedge phi2 restricted to W. And then we have that the lines which intersect L1 is the same as the zeros of sigma 1. So using the other three lines we have, we can get a section of a different bundle. So using L2, L3, L4, we can form an analogous section, sigma, of the direct sum equals 1 to 4 of S dual wedge S dual. Let's abbreviate this and call it V, and we have that the zeros of sigma are exactly the lines we're looking for. Then equals the L such that L intersect Li really intersects for I equals 1 to 4. Is this bundle relatively orientable? Relatively. The determinant of the tangent bundle is O of 4, and the determinant of V is the tensor product of these line bundles. So they're both squares, so yes. Okay, so let's do our recipe. We need to identify sigma with a function, so let's do that. So we're now going to So computing degree at some line L of sigma, we're going to choose some coordinates on the Grassmannian. For that purpose, we need to choose dimension 2 subspaces parameterized by A4. We'll do the lines which intersect phi 3 equals 0 and phi 4 equals 0. So let's let E1 twiddle equal, we're defining some new bases, E1, E2 twiddle equal E2, E3 twiddle equal X E1 plus Y E2 plus E3, and E4 twiddle equal X prime E1 plus Y prime E2 plus E4. And then we have an open subset of the Grassmannian from spec K, X, Y, X prime, Y prime, where the coordinates X, Y, X prime, Y prime correspond to the projectivization of E3 twiddle, of the span of E3 twiddle and E4 twiddle. So those are some coordinates. And then what does our function look like? That depends on our line, because sigma depends on our line. Well, actually, let's first choose a local trivialization. So the V can be locally trivialized when we locally trivialize the line bundle S dual, wedge S dual. So we'll say S dual, wedge S dual is locally trivialized we just take the dual basis. So let phi 1 twiddle, phi 2 twiddle, phi 3 twiddle, phi 4 twiddle be the dual basis. So this is trivialized by phi 3 twiddle, wedge phi 4 twiddle. These are compatible with some relative orientation. And then let's write sigma as a function, A4 to A4. This depends on the choice of lines, and it's not worth it to give notation for all of them. So we're going to just assume L1 is the span, is the projectivization of the span of E3 and E4, and then sigma is equal to sigma 1, and then some things that, and sigma 1 is phi 1 wedge phi 2, no twiddles, and we just haven't bothered making notation for these, so didn't bother making notation because it's the same. So we need to express this as a function of x, y, x prime, and y prime. So to do that, we need to know what the coefficient of phi 3 twiddle, wedge phi 4 twiddle of is in this. So that's an exciting linear algebra problem. And so we need to, so we've got phi 1 wedge phi 2 restricted to k of E3 twiddle plus E4 twiddle, and we need to expand it out and see what the coefficient is of E3 twiddle wedge E4 twiddle. So we want to know how many E3 twiddles there are in phi 1. So to do that, we can evaluate. How does this go? We can evaluate phi 1 on E3 twiddle, because that's exactly how many phi 3 twiddles we need. So phi 1 on E3 twiddle is x. So let's do this in some steps. So we've got x, E3 twiddle, plus y, phi 4 twiddle, wedge, x. It's going to be x prime now that we've done the hard thing once. It's just the other one, phi 3 twiddle plus y prime phi 4 twiddle. And so we see that as a function, we get x y prime minus y x prime phi 3 twiddle wedge phi 4 twiddle. So as a function from A4 to, well, we're just doing A1, so we've got sigma of x, y, x prime, y prime is equal to x, y prime minus y, x prime, and then some things we didn't do notation for. So then we have an explicit understanding of what this function is, so we can run computation of the local degree. So, take Jacobian, compute local degree. Dot, dot, dot. And that has something to do with a determinant of a matrix with functions like this. But to get a fun theorem counting lines, we'd like to know, is there an arithmetic, geometric interpretation of the big determinant, or whatever it is, the recipe with all of the x's and y's interpretation of the local degree. And because it's a big expression, maybe the best way to start on this question is to say what arithmetic geometric information is available. So what? Well, we have this line we're at, so P is a point on our Grassmannian, let's call it L, it's a line. And L, the projectivization of W, is a line intersecting L1, L2, L3, and L4. And in particular, we have 4 points on that line. So that means that L intersect Li is 4 points on L, which is isomorphic to P1 of K of L. And therefore, they have a cross ratio. So let lambda be the cross ratio. And there is another cross ratio here. So if the planes in P3 containing L, these are the dimension 3 subspaces V containing W, or so we want we've got V, W dimension 2 inside the field of definition of L or W to the 4. So this is like a one-dimensional subspace of K of, so equivalently V bar dimension 1 inside a KL2. So the upshot is they are a P1, isomorphic to a P1 K of L. And we have 4 planes containing L, namely the 4 planes spanned by the line. So the span, not in just the plane determined by L and Li for I equals 1, 2, 3, 4 gives is 4 points on this P1 K of L, and we can let mu be the cross ratio. And there was this choice of how the line, it wasn't the line that determined our section, it was equations cutting out the line. But if you normalize things correctly, then you can get that the local degree of this function sigma is the trace of k of L down to k of the difference of lambda minus mu. So then we get this fun theorem that says let L1, L2, L3, L4 be pairwise non-intersecting lines in P3, then the sum over L such that, well, there are different ways to get around this, but let's do characteristic not two, such that L intersect L, that L intersects all the lines of this trace of the difference of the cross ratios is a fixed form, and it is the hyperbolic form. There are lots of places to go from here, but, well, this is a better place to stop than trying to give a summary of where things are going now, so thank you very much.
Questions?
Could you give a summary of where things are going now?
So my favorite place things are going now is doing some Gromov-Witten invariants with Jake and Jesse. Mark Levine has a lovely paper on Welschinger invariants, which are also Gromov-Witten invariants. Why is that fun? We get away from some ones and minus ones. There are beautiful recursive formulas. There are connections with modular forms. There's a lot of fun enumerative geometry out there. Other places this is going, I should say that the project group, these are all, so you'll hear tomorrow, these are all lines defined over K. And if you put in a very cool correction factor that the project group found, you can, with some discriminants, you get another arithmetic geometric interpretation when these lines just have a K orbit. That can, that's coming. There's, similar to those Gromov-Witten invariants, there's counting like d-nodal curves in families, and Mark Levine has a beautiful count of one-nodal curves in a pencil. And Jesse and I have a count of two-nodal curves that's a little different. It's along the lines of an argument of Kleinman and Peony. Candace Bethea, who's a student of Jesse Cass, along with me and Jesse, did, so Mark Levine did a lovely Riemann-Hurwitz formula, and Candace has a cool extension of that, including some wild ramification and enrichment. And I've already mentioned how much I love Matthias's oriented Schubert calculus paper. But he's giving me that look like I've clearly talked too much. So I'm going to, I'll stop.
Further questions? Okay, let's thank Kirsten. And since this is her last lecture, let's especially thank her for a wonderful lecture series.